Okay, our next lecture is on electromagnetic waves in a dielectric medium. This is lecture 9B2. We already have the blueprint of this chapter, and I have already done introduction to one-dimensional waves. We have obtained EM waves from Maxwell's equations. I have described EM waves being supported and being propagating in vacuum. And now we are going into dielectric medium, where we'll do also reflection and transmission at the interface of two dielectrics. EM waves in a dielectric, which means it's also have charge-free and current-free lossless material, meaning there is no Ohm's law or there is no loss of energy because of traveling within the medium. That is what I mean by lossless material. If there are no charges and currents, then within the dielectric, of course, rho f or rho is zero, free charge is zero, and there is no current. So you can write down the Maxwell's equations. Divergence of D is zero, divergence of D is zero, of course, always. So, and this Maxwell's Ampere's law is still the same. And this one I write down as curl of H as a displacement current, which is del D by del T. Okay. Now let's assume that this is general in a material without charge and current. Now, if I assume there's a linear homogeneous media, okay, that I am dealing with, then D is epsilon E, and H, remember this epsilon is now the material's dielectric constant and not epsilon naught. And H is B by mu, where mu is the permeability of the dielectric. So now I can rewrite, if I using these linear equations, constitutive relations, I can rewrite the Maxwell's equations. D becomes still divergence of E is zero, and this of course has no change, is the Maxwell Ampere's law, and this is always true. What changes is actually in this equation, that is, I replace B by H by B by using this, and D by epsilon E, and hence del cross B is mu naught epsilon naught del E by del T. Recall that in vacuum it was only mu naught epsilon naught. Okay, so this is the only really change, only difference from what we had in the vacuum case. And what is that? That is simply 1 by c square, and here it is 1 by v square. So everything remains the same in dielectric medium, without charge, without current, except for the fact that the speed of the uh, electromagnetic waves get changed according to mu and epsilon. Okay, so then it's quite easy. We can take all our results that we have done for vacuum and just use it with the new velocity. So if in a dielectric media with a speed given by 1 by root over mu epsilon, which is nothing but c by n, where we define our refractive index as n defined as the ratio between epsilon mu and epsilon naught mu naught of course square root. Okay, and so in most materials, mu is simply mu naught, unless you are dealing with a magnetic material like a ferromagnetic or, okay, so most dielectrics will consider mu as same as mu naught. Then for dielectrics, the n is really root over of the relative permittivity. Okay, so if glass n is equal to 1.5, then we know the relative permittivity is simply square of that. All right. So then for dielectrics, there's a transcription that for the wave equations that you obtained for vacuum, replace epsilon by epsilon naught by epsilon, mu naught by mu, and of course the speed of light in free space or vacuum by v. Okay, so typically n is larger than 1, and hence the light propagates slower in most dielectric material. So the energy density simply changes by epsilon by and mu instead of epsilon naught mu naught. So it's the same expression. The Poynting vector, instead of 1 by mu naught, it's 1 by mu E cross B. The intensity, the time averaged of the magnitude of the Poynting vector. So this was C epsilon naught. Instead of that, it becomes now V epsilon. All right. So that is, of course, the boundary conditions are general boundary conditions. We'll have to, in this case, sigma f is 0 and normal of the B1 and B2 uh, remains the same. If there is a there are two dielectrics which you are going to consider. Okay. So this is the general boundary condition, and Kf is 0, and hence H1 is equal to H2, E1 parallel, H1 parallel is equal to H1, H2 parallel, and E1 parallel, of course, is equal to E2 parallel. And we are going to use these boundary conditions later when we meet an interface between two dielectrics. So reflection and transmission at a dielectric at normal incidence. Let's first take the normal incidence. Okay, that is easier to do. And so let's. This is dielectric 1, dielectric 2. This is normal incidence. So let's consider the electromagnetic wave with its incident EI polarized in the x direction, okay, and is traveling in the z direction. And of course, the right-hand rule will give us the incident magnetic field perpendicular to it like that. Okay, this is a triad. The K1 direction in which it is traveling. Then it hits this interface. What can happen? A little bit of it can get transmitted, and a little bit can get reflected. All right. So we have now, I have indicated the what happens, and then we can write down the uh, all the. So let's first thing is the boundary conditions will ensure that the frequency is the same. Okay, and is it traveling in the z direction, polarized in the x direction, approaches the interface from the left. Now let's write down all the incident wave. Incident wave, I am writing down in terms of incident I. This is vector, and I am using complex amplitude. So this is the complex wave. Okay, so it's the complex amplitude. So with E naught I, and the vector is taken up by that polarization. It's polarized in x hat direction. It is traveling in K1 direction. It's okay, and that is which is in z direction. Is traveling, and hence I can get the Bi, that is simply divided by the velocity of the wave in medium 1, and it is pointing in EO y direction. This y direction is pointing in y direction. So that's complete description of the incident wave which is traveling and going to meet the interface. Now, what is the reflected wave? Of course, okay, is the similar now R, except that now this K1, this is still in the medium 1, and hence K1 is minus. So it is going in the reverse direction, okay, and it is still polarized in x hat direction. And the B, we just get by a rule, is now it's going pointing in the minus y direction, so you pick up a minus here, and this minus of course comes from ER, and it is pointing minus y direction. So that's the reflected wave. And the transmitted wave going almost similar to the incident wave. Okay, so it is T for transmission, complex amplitude. It is now going in medium 2 in the z direction. It's still going in the z direction. We're going to transmit it. So it's K2 and is plus. Okay, and then of course we get the B, corresponding B, divided by now 1 by V2. 1 by V2, and this is now again pointing in y direction. So now all the three states, okay, we have the complete description of the wave, and hence we can calculate whatever we want to calculate in terms of energy. We are especially interested in what is the fraction of the energy that comes through this and hits it normally, okay, what is the fraction of energy or the fraction of intensity which gets reflected, and what is the fraction of intensity which gets transmitted. Okay, let's say medium 1 is air and this is glass. That's a typical air glass interface. Okay, So at z is equal to 0, we'll have to apply the boundary condition. Okay. So E1 parallel is equal to E2 parallel in this. Okay. And of course, B1 and B2 are normal. And then D1 is perpendicular, D and normal and D2 normal must be equal. Here the standard, all the four boundary conditions, I put that in the same box now. Okay. And we can now apply that. Okay. And that is, since z is equal to 0, okay, uh, that and then these conditions, the exponentials cancel away. Okay. And we are left with only the complex amplitudes. That's the advantage of using complex amplitudes. Okay. We don't have to struggle with trigonometric identities involving cos and sine and so on and so forth. Okay. So you could one could simply write down the amplitudes EOI plus EOR is equal to EOT, and that comes from here. Okay, from here H1 is equal to H2. Okay, so it's 1 mu1. So the EOI minus the one EO reflected one must be equal to the transmitted one. Okay, in terms of B, written down in terms of B, and then of course 1 by mu1 and mu2. Okay, so that's good. And typically mu1 is equal to mu2 is mu naught. If it is dielectric and is not a specifically magnetic material or is a nonlinear magnetic material, we are considering a typical normal linear homogeneous material. If it's a dielectric, then mu1 and mu2 can be considered to be almost equal to mu naught. It's not equal to, it's almost approximately equal to mu naught. Okay, and let's consider that. Once we do that, after that is simple algebra, you can obtain the fraction of the reflected energy, which is the intensity of IR divided by incident energy. And what is that? That is simply proportional to the amplitude of EOR. We have gotten in terms of EOR, EOI, and EOT. Now I'm just taking the ratio of EOR and EOI and squaring it. Okay, and you can show that that is simply nothing but if it's N1 and N2 are the refractive index of medium 1 and N2 is the refractive index of medium 2, then the amount reflected at normal incidence is simply this ratio, N1 minus N2, okay, divided by N1 plus N2 whole square. Suppose it is, let's say N1 is air and N2 is glass. So N1, this is 1 minus 1.5, so point half, and half divided by 2.5. This is 3 by 2. Okay, so only that much fraction of energy. Okay, half divided by 3 by 2. So it's like this is sorry 5 by 2. Okay, so this is like 1 by 5. Okay, so 1 by 5, so 1 by 25. Okay, so it's like 4%, which is getting reflected, okay, of the energy that is coming in. And what is getting transmitted is similarly one can show. Of course, this is now a ratio of, and that is why we get in terms of N1 and N2, and it is now 4N1 N2 divided by N1 plus N2 whole square. Okay, I would, and you can show that since it is lossless medium, that it is in this R plus T is equal to 1. Okay, so the reflected and transmitted must be equal to 1. That's simply energy conservation. Now, I did not do the algebra because algebra is very simple. Once I have these equations and I know all the incident waves from the, and z is equal to 0, the boundary condition, it is trivial matter to get this relations for reflected intensity fraction reflected and fraction of energy or intensity transmitted. Okay, so please prove this. Okay, I might ask you to do that, and it's very useful to remember also in actual application. The normal incidence is a very you will encounter this very often in many situations. Okay, so let's look at the reflection and transmission and dielectric interface, but with now with oblique incidence. Okay, that is now the incident. This is incident angle. So incidence is with ki. This is the direction of ki, and it is getting reflected theta theta r, and it is getting transmitted theta t. Is kt is transmitted wave, and this is the plane and it still is traveling in typically in Z direction, okay, though it in angle. Okay, so let's look at a plane wave, of course, frequency omega, traveling in the k incident direction, ki direction, meets the interface. Okay, and so the way I've described, so the incident wave now still vector, complex, complex amplitude, and vector I ki. Now, okay, so I cannot write down k1 dot z. So it could be any r. So we have generalized into ki is the general direction in which this is traveling. Okay, and so ki dot r is now tells you the this is equivalent to k1z if it was normal. If it is not normal, you take the dot product. Okay, of the r at any particular position you want to find out, then at r, then you take its dot product in the direction of ki. Okay, so that is how this is described. Of course, once I do that, remember, so bi at any r. Okay, so this is 1 by v1 and the triad, the right hand triad, ki direction hat cross ei. So that's give me bi. Okay, so then the incident wave, that was the incident wave. Now I can write down similarly the reflected wave. So reflected wave r of t, similarly ei, still kr. Kr is the direction in which it is traveling, dot r minus omega t. This is the complex amplitude along with the vector, the polarization vector included here. Okay, this is the amplitude. And similarly, I will get the magnetic field 1 by v1, kr. This is still in medium 1, so kr e r, okay, across er is hat. The transmitted one, okay, is similar. Transmitted rt e0t e to the power I kt dot r minus omega t, and then brt is simply 1 by v2 now, because it's now medium 2, and kt is the direction in which this is traveling, cross et. So now we have given a description of the incident wave, the reflected wave, and the transmitted wave, okay, at an oblique. Uh, Now it is important to understand that boundary conditions must hold at all points on the plane for all times. Okay, and hence this exponent at the boundary, these exponentials would not would be all be same. Okay, okay. So then we have to only worry about the amplitudes. Therefore, the exponential factors, okay, must be equal at z is equal to 0 plane. Okay, so we have taken care of that. Okay. Now, and because of that, I can write down that the ki dot r must be equal to kr dot r and kt dot r for z is equal to 0. If all these exponential factors have to be the same, which means at z is equal to 0, ki dot r and kr dot r and kt dot r must be equal. And that immediately gives me, I can write down, is actually what it means, x ki, x from the incident, okay, and y ki y must be equal to so on and so forth. Of course, z1 is not there because there is no z component. Uh, okay, so uh, I can write down from here to here because z is equal, at z is equal to 0, they must be equal. And because of that, now I can write down, so that is kix, krx, and ktx. Okay, if y is equal to 0, then okay, this must be true. Okay, so directly from here. So because of that, I can write down that ki, what is kix? Okay, is ki sine theta I must be equal to kr sine theta r, okay, equal to kt sine theta t. And that will give me, first thing is ki sine theta I and kr sine theta r, okay, and hence theta I must be equal to theta r. Okay, and so that is the law of reflection. That, okay, and the same thing we'll also can get obtained from the relationship sine theta t is equal to sine theta I is n1 by n2, and that is law of refraction, which we learned in in our upper primary or in high school. Okay, now we have gotten these results from electrodynamics or from Maxwell's equations, okay, which you had just taught as a simple law given to you. Now, once given that, our goal is to find out, and I'll just state the result and I'll tell you how to do it. So we are again looking for what is the reflection uh, fraction, okay, the intensity of reflected intensity, the ratio of the incident intensity, which is nothing but EOR, the real magnitude by EOI square, okay. And this can be expressed just like N1, N2, and N1 plus N2, except now now alpha and beta now come because of the angle. Okay, so cos theta t by cos theta I, and beta is mu n1 n1 and mu 2 n1. So theta I is equal to theta r, but theta t and theta I can be different. Okay, in fact that's the diffraction angle, and so that defines alpha, this ratio of the two angles of the incident cos theta t divided by cos theta. There's a definition, all right. And beta, it is instead of being simple ratio of n2 by n1, which reduces. Suppose you take mu1 is equal to mu2, then beta is nothing but um, if the two dielectrics have same mu, which is likely to have is almost equal to mu naught, then beta is the ratio of the refractive indices, and alpha is the ratio of the angle of the transmitted angle and the incident angle. Okay, their cosines. So, and you can obtain this. This is very easy to obtain. Okay, so please prove this. But I'll show you how to do it. Okay, I'll give you steps. But this is what we're looking after. Okay, this is our aim. So I've summarized everything that we need to be able to deal with oblique incidence. Of course, I have assumed that there's a plane of incidence. I'm going to tell you that. So how to use the boundary condition? Okay. So let me, the first one that I'm doing is polarization, which is in plane of incidence. Okay, that is in the very plane in which it is incident and reflected. The polarized is also in the same plane as the incidence plane. Okay, of course, all three waves, that is incident, reflected, and transmitted, must have the same frequency omega. Okay, otherwise boundary conditions cannot be solved. So omega must be ki v1, kr v1, and k2 v2, and so k's can be related like this. Must have same omega, and hence I can write down k1 v1, kr v1, v2 by v1 kt, and which is nothing but n1 by n2 by kt if mu1 is very close to mu t. Okay, so now this is the situation that I have. So plane of incidence would mean what? Okay, that is my E. Normally when it says polarized, we only refer to the direction of the electric field as a convention. Okay, so the incident beam is traveling in this direction, and the E is in the same plane of incidence. The other possibility is E could have been perpendicular. That's one something which I'll let you work out. Okay, so now this is so EI is pointing in this direction, and then it's going, reflected one is pointing in the same plane. All right, and yeah, this is reflected and the transmitted. So this is the case of polarization in plane of incident. Okay, and uh, the old boundary condition. Okay, and the I've written down our old, the original boundary condition is always good to get the relation to the boundary condition, which is um, our original boundary condition. And if I now specifically, I can write down now epsilon 1, okay, the fraction which is inside, that is IR, this is EOI plus EOIR, it must be, okay, epsilon 2 EO2 is the Z component, simply BOI, this is BOR, this is BOIT. So incident and similarly the EOI, EOR, this is a typo here. This must be the reflected one, and this is also reflected one. X of Y is E of T, and so it is just writing down ky is equal to 0 and doing that. Okay, so this is a mistype here. These are all reflected ones because this is in medium 1 and this is in medium 2. Okay, and then I'll correct that in the final form. Of course, now, so this also should be UIR sine theta R. I had corrected that. I don't know why. All right. So then this relationship is now, so this is UI sine theta I, UR sine theta R must be equal to epsilon 2 minus EOT sine theta T. All right. So that's the boundary condition that is satisfied. No contribution since from this boundary condition, no contribution since magnetic fields have no Z components. Okay, because it's traveling, it is a transverse wave. Okay, this would of course give us UI cos theta I plus UOR. This is correctly written here, cos theta R plus UOT cos theta T. Okay, so this will also be UOR. All right. So and then from this we would get our the condition from EOI and EOR. Okay, simple, the boundary conditions. Now, using this relationship, okay, we can now we also know can define now alpha and beta as we had done that. I just done that. If we now define to make the algebra simpler, if we define beta and alpha like this, then I can write down from this and this would reduce to ui minus ur, which is beta UO2. Okay, and this one would give you ui plus ui is alpha UOT. Okay, so two simple conditions. This is the complex amplitude only. Okay, so complex amplitudes ui minus ur and ui plus ur in terms of alpha UOT and beta UOT. Okay, once you obtain that, it's simple to get the solve for the EOR, which is alpha minus beta plus alpha plus beta UOI, and UOT is 2 by alpha plus beta UOI. Now these are called the Fresnel equations for this particular case. There is another case in which E could be perpendicular to the plane of incidence. There are two such relationships which come there, and all four are called Fresnel conditions. But these two are Fresnel conditions for this particular case, which polarization is in plane of incidence. So Fresnel equations for parallel incidence. I've just mentioned that. So now uh, uh, realize that the transmitted wave is always in phase with the incident wave. Okay, but the depending on the alpha and beta, UR and UI, okay, would whether it is plus or minus, that will depend on the relative values of an alpha and beta. Okay, for the reflected one, if alpha is greater than beta, then of course they are in phase. Okay, because alpha and this remains positive, so the amplitude of UR and UI are in the same sign. But if alpha is less than beta, okay, then it is flips. Okay, it's flips by 180 degree. That's out of phase. It is minus. Okay, it comes out of these Fresnel equations directly. And but EOT and EOI, okay, the transmitted wave and incident wave are always in phase. Okay, because this is always a positive quantity. So let's look at something that comes out of this particular case, or plane of incidence, is called the Brewster's angle. Now you can see that the what controls the quantity of the reflected and transmitted is relative values of alpha and beta. Okay, suppose alpha is equal to beta. Okay, sorry, Brewster's angle. So the amplitude of the transmitted and reflected wave depend on the angle of incidence, okay, because alpha is a function of incident angle. Okay, you remember cos theta I by cos theta t by cos theta I. Okay, so alpha is cos theta t by cos theta I. So alpha and beta depend upon the angle, and beta is of course just this. Okay, so now let's express. Uh, so EOR, I'm just rewriting what I showed you last time. Okay, so now this alpha and beta depend. Alpha will especially will depend on angle of incidence. Okay, so let's write down that. I can write down case cos theta t as root over 1 minus 1 by 2 sine theta I square by cos theta I. Now, if it is case of normal incidence, okay, theta I is equal to 0, this becomes 1, okay, and then alpha becomes 1. All right, that's the normal incidence. That's the first case that we actually solved. So all the results would be same if you put theta I is equal to 0. Okay, this alpha is equal to 1. If theta I is 90 degree, then alpha diverges. So you get total internal reflection. So the whole thing is totally reflected. If it is grazing the surface, then alpha goes diverges. Okay, and it can cos 90. Okay, and it is completely reflected. Okay, total internal reflection. When alpha is equal to beta, okay, that's the case. There is no reflection because alpha is equal to beta, so EOR becomes 0. Okay, and for that specific angle at which alpha is equal to beta, because alpha depends on the angle of incidence, is called the Brewster's angle. Okay, so and you can show this is for air glass system. Air is 1 and glass is 1.5. What is this fraction? This is EOT by transmitted. Okay, and is uh, the reflected, right? So you can see that this is complex amplitude. Okay, so this is it is negative below the till. Okay, so alpha is clearly less than beta, and that's why UO R is reflected one is negative, and that is negative till alpha is equal to beta. At that point there is no reflection, it's 0. Okay, there's only transmission, and that is why it's an important angle, because you can see that this particular polarization, okay, uh, uh, polarization does not get reflected, which means whatever gets reflected must have the other polarization, okay, which is the perpendicular. And hence you can get a polarized light simply by reflection if the angle of incidence is chosen to be the Brewster angle. All right. So that's something that we'll also discuss probably later. So for air and glass interface, this happens at this angle of theta in incident angle. So we can solve that, okay, for any general case. Sine square theta b, I can write down Brewster angle. From here, it's 1 minus root of 1 minus beta square n1 by n2 beta square. Because I'm assuming typically mu1 is mu2, so beta is equal to n2 by n1, okay. Beta is simply n2 by n1 because mu1 is equal to mu2, which is a typical case. And sine square theta b then can reduce to beta square by almost approximately equal to beta square by 1 plus beta square, which can now be converted into tan theta. So tan theta b is nothing but n2 and n1. So Brewster's angle for any two pair of dielectrics can be simply be obtained by n2 by n1. So for air glass interface, tan theta b must be 1.5, and so theta b is tan inverse 1.5 if n2 is 1.5. That's how you get this angle so simply. All right, but this is a detailed calculation, but you can obtain Brewster's angle for two dielectrics in which you make these assumptions that mu1 is equal to mu2, and you can obtain directly the Brewster angle. Okay. Now, this is one of the characteristics of the solution. But let's look at the actual energy, the solution that I've given. Let's look at that side. Okay, I'm rewriting that. Okay, the amount that is reflected is EOR EO by square, alpha minus beta by alpha plus beta whole square, and transmitted is IT by IEI, and so this is EOT by EI square. And of course, the cos is there, and this is in terms of alpha beta, 2 by alpha plus beta. Okay, and the intensity is of course in vacuum. This is in vacuum. I know what is the intensity. This is C epsilon naught, and in dielectric it will get modified. For incident intensity is of course V1 E1 UI square. Now this cos theta is there because the angle of incidence is still there. Okay, so in this expression, the intensity expression, I have the cos theta I. Okay, so similarly, now I can write down the reflected intensity V1 U1 UR square cos theta R, and the transmitted intensity V2 E2 UT square cos theta T. Okay, so this is in vacuum. This is in the oblique incident case, and then this is already I've shown you the calculation for the EO T by EOI, and EO R by EOI is uh, behaves like that. So if theta is equal to 90, of course, then reflection is the transmission is 0, and everything gets reflected. Okay, all right, and only a small fraction gets and small fraction waits a change in phase. Okay, below Brewster angle for this particular case. Okay, then one can take square of that and simply plot that. So this, for example, becomes square, and then you can see that this is the reflected amount, and that reflected amount, since this decreases, the reflected amount decreases, and at Brewster angle reflection is 0, and then reflection picks up. Okay, and transmission is similarly there, right? So here at Brewster angle, a reflected quantity is 0 and transmitted is 1. Since there is reflection, transmission is smaller, and of course R plus T is equal to 1. So this is a calculation for air glass interface with glass N is equal to 1.5. But given these equations, it can be easily be done for any particular pair of dielectrics. Okay. So with that, I come to the summary. Okay, so we have actually gone from electrodynamics to optics, basically. Okay, we got even Snell's law of refraction, law of reflection. So let's summarize. In a lossless dielectric, where I'm saying there is a no loss of energy, EM waves are supported with a smaller velocity, and we obtain the refractive index of the medium. All right. Um, then at normal incidence, the reflected and transmitted wave depends on the refractive index of the medium, obviously. Okay, we recover the laws of reflection and refraction on applying of boundary conditions that we have learned, and we use that to. So the other case that I have not done, I would ask you to do it, so that you have full practice of how to use these boundary conditions. If E is polarized such that that is the case that I did, is parallel to the plane of incidence, we obtain the amplitude and incidence as a function of angle of incidence. Okay, amplitude and intensity, not incidence, as a function of angle of incidence. For the case of parallel polarization, which I did, there is a Brewster angle, and there is no reflected wave. A randomly polarized beam therefore gets polarized on reflection at that particular angle. A random polarization meaning there is a fraction which is in parallel direction. You can always express it as a part which is in parallel incidence and perpendicular to incidence. Okay, but the parallel component simply gets extinguished if the angle of incidence is same as the Brewster angle. Okay, and hence the reflected wave will have only the polarized. It's a small fraction of energy, but whatever energy you would get at that angle would be polarization would be perpendicular to the incidence plane. Okay, so I will ask you to work out the other case when the incident beam is polarized perpendicular to the plane of incident, and this is the case. Okay, so E is perpendicular. Is now I'm showing B here. It comes and then mm, uh, gets reflected and refracted or so this is, in this case I have shown the interface here. So this is comes here, and then this is the angle of incidence. We know angle of incidence is equal to an angle of reflection. That is general. So both these would be the same. Okay, and then this is the transmitted wave. Okay, but now E is perpendicular. B is in the plane of incidence. This is a separate case. For example, in that case, you will see there is no such thing as a Brewster angle. So I have left that as a problem in the home assignment, either in the practice problem or in the home assignment. Please work that out, and then the quantities that you're dealing with will become clearer. With that, we close this for this week because you have a lot of things to work out yourself. Okay, and I'll take up the other cases of conductors uh, and other phenomena associated with wave travel of dispersion and absorption in the next week. Thank you.